And so let me, okay, I'm recording now. Let me share this screen. Okay, so do you see my screen? It says workshop 5.
Yes.
Okay, so well, thank you very much for attending this workshop. So on behalf of the organizer, I welcome you to this workshop 5 devoted to data-driven science. And I would like just to describe in a few words the program of this workshop. As you see here, the workshop consists in 2 sessions, which in turn they contain 10 presentations, 10 talks, 6 of them in the first session and 4 of them in the second one. And this session will cover various topics ranging from application of data science, for instance, in astrophysics, health, biology, well, among others. And also we are going to discuss about certain application of certain techniques or the techniques itself that are in the core of the data science, such as natural language processing, parameter estimation, deep neural network training, among others. So after these talks, the workshop will end with a roundtable where the participants will talk about their experience and research around the fundamentals of data science or the application or use of data science tools. And also, we asked them to talk about some possibilities, for instance, of collaboration between Chile and France around data science. And of course, after this roundtable, we will open this discussion to all participants in this workshop. So, well, without extending this introduction more, I leave it with you, the chairman of the first session, Jean-Stéphane Deschamps. He's professor at the University of Paris North, Sorbonne, and deputy scientific director of CNRS. So, Jean-Stéphane, I finished to share, and now you are the boss.
Thank you, Hector. So I recall that each speaker has 15 minutes, and we have said 10 plus 5. So please try to be short enough so we will not have to run after time. The first speaker is Vincent Calves. Vincent, have you here?
Yes.
Can you try to share your screen, please?
Yes.
So Vincent is from CNRS at Université Claude Bernard in Lyon, and he will speak about self-generated gradients in biology. Thank you, Vincent. The floor is yours.
Thank you very much for the invitation. So I'm really glad to have this opportunity to present a glimpse of my research program. So I'm very interested into waves and the collective motion of microorganisms. So these are, for instance, bacteria. It can be bigger cells. And I try to give you something which is very important to me is about the role of the data, of the biological knowledge to drive mathematical research. So I will be quick on time. And let me first show you one example of this wave. So here you see a channel, so it's a microfluidics, so it's a small, very small scale, and you see in purple a wave of density wave of bacteria, so roughly 10 to the 5 individuals, and they move together. You see the same channel at a different time, at successive times, and they do so at a constant speed with a constant shape. So it's a very, very nice experiment, and it's a very nice mathematical equation. So I do not manipulate myself massive data, but the collaborators I'm working with, they have access to tracking of individual trajectories. So there are really a lot of data, and this informs a lot of what kind of model you can do and what kind of model is informative for the biology. So I'd like to present first one case study. So it's my first point, so about waves. And if I have time, I will present the second one. And each time, what is important is to present the experiment, so and the type of data, and also the type of model. So it can be a macroscopic model, so you just look at the density in space, and you look at the PDE, which is good for this. Which is appropriate for this biological question. And then if you have more data and if the macroscopic problem is not satisfactory, you can move to a finer scale, like a mesoscopic and even microscopic models, but I won't have time to speak about that. So let me first move to one very remarkable example of collective motion in an organism which is called Dictyostelium, which is considered as a biological cellular model, very used in biology. And here what you see at successive times, first a cloud of cells in the first picture, and then after some time you see a ring of density ring of cells. And if you look for even for days, you can see the ring moving outwards. And again, it does so at a constant speed and with a constant shape. So the question is, what kind of model can you design to explain such a remarkable phenomenon that can span for days? And I will rely on PDE and parabolic models. And the model will be a kind of diffusion plus something, depending on the data, on the knowledge. And the question is, can you find a wave? And can you compute the speed, c, and the profile, rho, for this wave? So let me give you a glimpse of the experiment. It's a very simple experiment, yet it's quite a recent one. So you have a layer with a medium. You put a layer of cells initially at the middle of the plate with some medium, and then you cover it with a glass, which is not permeable to oxygen. So oxygen can only come from the outbounds. And it means that it will have a very limited, cells will have a very limited access to oxygen. And what happens is they grow, the colony will grow slowly. And after some time, it will consume the oxygen, which is in the center of the colony. And then it will be now an hypoxic region, so with a very low concentration of oxygen, roughly, it's below 1%. It's really like, it's really a very small amount of oxygen there. So cells here are trapped. They can hardly move. They cannot divide anymore. And then the ring of cells that have access to oxygen will grow. And the question is to understand what are the mechanisms behind. So it's a very simple setup. It leads to a very remarkable outcome. This was done previously for cancerous cells in Lyon at some cancer research center, and it was reproduced with simpler organisms, those Dictyostelium cells. So again, what can you see from above? And as you see, you see the cells in the video microscopy, so you can really track trajectories, and depending on where they are relative to the ring, you can see different behaviors, and you can build up a model. So here is the data to show you that it's really a nearly perfect ring. So if you look on the left picture, this is what's called a chemograph. So it's essentially a section of the picture where you have time on the ordinate and space in abscissa. So we see after some time you have a constant line. So it means that the ring is moving in space at a constant speed. What is the mechanism behind is essentially that very simple mechanism. This is our minimal model, minimal hypothesis. If there is enough oxygen, the cells will divide. And it is known that cells which divide and diffuse, this produce a wave, but a slow one, because it's only driven essentially by diffusion. And below some threshold, we'll try to keep pace of the oxygen gradient. This is what is called a self-generated gradient, because they consume oxygen all along the way. And they try to migrate in the direction of the gradient. So if oxygen is enough, they are blind to oxygen, but they use energy to divide. And if it's below, then they cannot divide anymore. This is our hypothesis, and they migrate. So this is consistent with the observation of the tracking of cells. And you can build a very simple parabolic model. Yet quite original because of this dichotomy between the two phenotypes. And very importantly, you can find an explicit formula for the speed. So then with this formula, you can understand what is the role of each parameter, diffusion, growth, and directed motion in the collective motion of the population. And then you can, of course, it's very rough, but still, then you can try to see what is consistent, what is not, and try to enrich the model by discussion with a biophysicist. So this was published in some journal. I think I forgot to mention. Yes, it was published recently in a biological paper, the journal. So my second example, where I will have a finer scale, is about Escherichia coli, which is a bacteria part of our intestinal flora. And now we have a finer scale, so we can really look with more structure, and we can count the density not only in space but also in direction. How many cells move at each position into this direction? So now X is a position and V is a direction. And again, you ask the question of, can you construct and you prove existence and characteristics of waves? So this is an old story. It dates back to Julius Adler. This is a science paper in '66 with exactly the same problem. Sorry, and this is let's say a modern picture of it. You see on the top the wave of bacteria again, so it's the same as essentially the same as my very first picture on the first slide. And below you can see reconstruction of trajectories. So you see the massive data that you have access to. And in green you see there is one single trajectory has been picked up. And you see the bias. Each bacteria has a tendency to move to the right. So of course, collectively, this makes this wave of this population wave. So in a very short, in a nutshell, you can have again a sort of diffusion advection model to explain the population wave, and you have again a very simple formula for the speed c, which is on the bottom of the slide. So it depends on the parameter, how preferentially you move into what direction with one gradient. How the gradient is built up, how it diffuses. So you have, let's say, a biophysical parameter, but again, you have a very simple formula. So then you can, again, address the question of what is the importance, the relative importance of each phenomenon into that. What is important, maybe something which I'd like to stress out, is that those populations, so they navigate in a heterogeneous environment. So there's either oxygen, there are nutrients, they also communicate between each other by diffusing, by releasing some diffusive chemical. So really the environment is moving together with the population. It's really a coupled system with a population of cells and a dynamic environment created by the cells. So you can validate your model on the experimental data. So again, the same chemograph, now reverse in time and space. And this simple model is not enough to encompass all possible experimental settings. So you can enrich it and look at a finer scale. Well, now you have a kinetic transport equation which follows the density like in statistical physics in the kinetic theory of gases, where now, but you see not the molecule, but you see the bacteria moving. And you can prove that there exists wave for this now, let's say, more refined, more complicated model, but you lose the simple formulas because it's less explicit, let's say. But still, you can validate an experiment, and you can see that the model reproduces nearly perfectly the wave because you have included a lot of individual microscopic details into your mesoscopic model. So, few conclusions. So, I think it's very important to discuss with biologists, as you know, many of you, because this fertilizes mathematical research, and in turn, mathematical analysis as tools to address questions quantitatively, and this facilitates interaction, very fruitful interaction with biologists. And what is very important to me, and especially in the context of this workshop, is to pinpoint that data are really essential to design the appropriate model. The more information you have, the more refined you can be. But sometimes, if you have let's say rough information, a simple model also can do the job. Thank you very much for your attention.
Thank you, Vincent. Are there any questions? Eduardo?
Yeah.
Yes, I've seen you.
Vincent, do you have some, I didn't see it, maybe it was my mistake, Do you have some estimation of the speed at which this traveling wave exists?
So on the biological side, yes, it's about if you look at the chemograph, for instance, this blue background picture is the density. So it's an optical density of the video microscopy. So the red part is really the dense population of cells. And you see that here, for instance, it's a 1.8 micrometer per second, which is roughly 10% of the individual speed. Bacteria are moving roughly at 20 micrometer per second, each individual. So the collective motion is 10% of it. And on the mathematical side, depends on the model. So for example, in this for bacteria, in this simple case, you see that the speed C must satisfy a reasonably simple equation, but you can even further solve if you like. And it's essentially a balance between two signals that the cells are responding to. So one signal, they try to move to the right because there is more nutrient there, because they have consumed most of the nutrient behind the wave. So they try to move ahead to find more nutrient. And second, they try they would like to stay together, to stay confined, because they communicate between each other. So these are two signals, it's two responses which are balanced, and this is exactly the meaning of this equation. If you go to the simpler experiment, where there is only one oxygen gradient, then in this case it's even simpler. The speed is just it's essentially a geometric mean or harmonic mean between the various parameters you have in your model. Okay. And I don't have time of course to elaborate, but there are many interesting outcomes from these formulas. These formulas, they contain a lot of conclusions that are interesting for discussion.
Sure. Thank you, Vincent.
Thank you.
Yeah. Thank you, Vincent. So we have very short time. If you want to have question, to ask question, of course, you can email the speakers.
With pleasure.
Anybody for a short question? Very, very short. If no, we can switch to the next speaker. Can you unshare your screen, please? Thank you. The next speaker is Ezekiel Treister. Are you here?
Yes, hi, good morning.
Okay. So Ezekiel is from Católica University in Chile, and we will switch to astrophysics, and he will speak about data-driven science in astrophysics in the context of the Center for Astrophysics and Related Technologies. Can you try to share your screen?
Yes, please let me know if this works.
Yes, it's okay, it works. So,
okay, excellent.
The floor is yours.
Okay, excellent. Thank you very much, and thank you for the opportunity to present in this forum. It is actually very timely and very exciting, because this is the first time that we are presenting the second stage of the Center for Astrophysics and Associated Technologies, or CATA for the Spanish acronym. And I said it's very timely because it's only as of a few days ago that I'm free to talk about it and present it now that is official that this is happening. So first, let me give a little bit of introduction. Basically, I know we keep talking about it and we take it for granted, but I know it's not obvious for everybody. But the Atacama Desert is one of the most important natural laboratories that we have in Chile, both in the ground, the desert itself, but also on the skies. I can very confidently say now that Chile has some of the best skies on the planet for astronomical observations, and those are the skies above the Atacama Desert in the north of the country. And this is due to the very unique set of conditions that allow to have not only very clear nights, basically almost every night is completely clear in the Atacama Desert, but also a very stable atmosphere, and more importantly, a very dry atmosphere that basically allows for very pristine, very unique opportunities for astronomical observations. Now, this is something that we knew for many years, and in fact, because of that, is that now Chile hosts some of the largest and the most advanced telescopes in the world. Here we can see some examples, and in fact, probably more relevant for this forum, most of the telescopes from Europe, the ground-based astronomical observatories from Europe, are installed in Chile as part of ESO, the European Southern Observatory, in particular the very large telescope in the Paranal mountain, and several other. There are in fact about $5 billion, so 5 times 10 to the 9 dollars in astronomical instrumentation currently installed in Chile. And this is only the beginning. This is not stopping here. And in fact, in the next years, in the next decade, there will be something like 60% of the total astronomical capabilities, ground-based astronomical capabilities, will be installed in Chile. And this is also thanks to several key projects that are currently in construction and that will be starting operations in the next few years. So because of that, Chile has a unique opportunity and plays a very important role in the development of astronomy. Now, because of most of these observatories are built by international consortia, but because of agreements with Chile, Chilean astronomers have the access to about 10% of the total observing time in each of these observatories. And while 10% might not seem like a large amount, it actually makes us Chilean astronomers very, very lucky in terms of access to observational resources. Now, this is at the same time a very unique opportunity, but also a responsibility. Of course, our first and most important responsibility is to make very good use of this unique natural resource to carry out world-class astronomical research. But more importantly, we need to make sure that we can extend the benefits of hosting these large observatories to the whole society. And that's more or less one of the main goals and the main motivation for the Cata Center. The center was first funded in 2008 for 10 years initially, and then extended for another 3. So it just finished the first stage of the center a few months ago. And now, when I was saying that this talk is very timely, it's only a few days ago that we learned that it was recommended for funding as part of the basal funding program by our investigation and development research for another 5 years, renewable for another 5 years. And in fact, I'm very happy that also the CMM, another center of this kind with whom we have very close relation, was also recommended for renovation. And the funding level is about $2 million per year that we are going to get from this government funding. Our center is composed of 15 main researchers coming from 5 universities in Chile, and 41 associate researchers. When you put them together, makes about 1/3 of all the astronomers with permanent positions in Chile. So it's very representative of the community, of the astronomical community as a whole. And it spreads over 12 universities going from the north of Chile, very close from where the telescopes are hosted, all the way to the south end of the country. Now, one unique feature of this program and of these centers, all these basal centers, is that in addition to carry out outstanding research, they also need to connect with the industry and to benefit the society as a whole. And that has been a key motivation of the first stage of the Cata Center, and now it's even perhaps even more stronger and more expanded than before. In the first stage, we mostly focus on instrumentation, on astronomical instrumentation development, and we base our connection with the industry on that. And more relevant to this workshop, we have now extended this approach, also because of the conditions and these new projects that are coming, to data-driven science and to data analysis and big data, machine learning, and so on. And we think, and we are going to focus our efforts on expanding not only our research, but also our connection with the industry in this sense. Obviously, the opportunities, once you're analyzing data, we are obviously counting stars and galaxies and astronomical sources, but of course you can expand and you can use some of the same techniques. You can take them to the industry, in other applications, and basically expand our range that both our center has and the training that we could provide as the part of the center. So with this idea in mind, we created inside this second stage of CATA a computing and data analysis nucleus, which is mostly aimed to support, to analyze, and to process large amounts of data, which are very well in line with the new observatories that I described before, that are coming and that are going to produce tens of terabytes and probably even more per night that will require to be analyzed. We will use this opportunity to connect with the industry, and I will describe in a second specific connections and agreements that we already signed and that we would like to expand in these 10 years of the project, and extend also the analysis tools that we will develop to analyze astronomical data. So I mentioned some of the key partnerships that we already established. We are going to use the resources, the computing resources and shared resources with the NLHPC, the National Laboratory for High Performance Computing. We already signed agreements. Some of the analysis will be done in the cloud, in particular using the Microsoft products and the cloud, and sharing expertise with our engineers, providing internship opportunities for our students, and hence increasing the connection with the industry. We're going to, well, probably I will not have a lot of time today, but we will have a key connection with machine learning tools, and we are going to develop machine learning techniques to analyze our data that can be extrapolated and so on. And a key factor, just to finish, a key factor in this new development is one of these new observatories that are going to be installed in the next decade. Actually, we hope that it will start scientific observations in 2024, which is the Vera Rubin Observatory that is currently in construction in the north of Chile, in Cerro Pachón, that is going to obtain the widest and the deepest and the survey of the sky, covering about 1/2 of the sky visible from the southern hemisphere, to limits to depths that are certainly unprecedented for a survey of this size. Now, this is a revolution and a completely new way in which we will do astrophysics. It's going to have catalogs. It's going to detect billions, tens of billions of sources in the 10 years of operations, stars, galaxies, solar system objects, etc. And in fact, I know Francisco is going to talk later on about ALERSA, which is of course deeply connected with LSST as well, but is mostly focused on the transient universe, which is of course one of the key goals of this project, but also it will generate a giant massive database of basically all or most of the objects visible in the southern sky, and create a gigantic database of something like 15 petabytes and an image collection of about 500 petabytes. Now, of course, analyzing this data will be a huge challenge, of course, that we'll approach, but also will create many opportunities science-wise. Basically, most of our scientific goals will be impacted by these observatories, but at the same time will allow us, as I was saying before, to create the opportunities to develop new algorithms, to analyze and classify the large amounts of data, will allow us to compare with cosmological simulations and to study topics like the nature of dark energy and dark matter, and basically study sources all the way from very early universe all the way to the solar system. And of course, this will open a new window. It will be one of the key scientific topics for our new, for the second stage of the Kata Center. And I'm happy to take questions about it because I know I'm running out of time now. So thank you very much.
Okay, thank you. Are there any questions? So I recall that you can raise your hand or write question or write the question in the chat if you have. Hector, you're speaking and you're mute. Okay. So perhaps I have a short question. So it is, we're speaking about the collaboration between France and Chile. Can you say something about your connection with the French researchers?
Yes, there are several, well, there are already many existing collaborations with French researchers. I mentioned mostly about Vera Rubin, but we also work together on ALMA projects and others. We do have, and I know that our director is here, Felipe, and we have a collaboration. We have a collaboration program specifically for astrophysics that is called. It was called UMI. Now is the French Chile something acronym. Sorry, I forgot the acronym. But we do have extensive collaborations. We receive French researchers very frequently. We do have a exchange program, and so we would like to continue those, and they are part of the center as well, of course. And we hope that we will increase and continue these collaborations through this center.
Okay.
Yes.
Yeah, I just posted the webpage of the center on the chat if you want to see.
So if there, so please visit the website indicated on in the chat. If there is no more question, we can switch to the next speaker. The speaker is Vittorio Perduca. Vittorio, yep. Okay, you share your screen, marvelous. And Vittorio is from Paris, Université de Paris, and he will speak about COVID-19. Please, Vittorio.
Thank you very much for this opportunity to intervene in this interdisciplinary workshop. I'm going to present an ongoing work together with fellow mathematicians Antoine Chambaz and Etienne Birmelet, and medical doctors at Hôpital Bicêtre, a large university hospital nearby Paris. So in this project, essentially we have two goals. The first one is to develop a score to predict the outcome of COVID patients based on their clinical information. And the second goal is to define the importance of covariables, which are important in the evolution of the disease, and then to estimate these measures. Let me start by give a few insights about the data. So we have around 200 data points, data about 200 patients. These data were collected during the first wave in March and April 2020. And we have information about demographic variables and clinical and biological variables as well. So this is just a selection of the variables. In total, we have around 50 covariates. So I said that the goal was to predict the outcome. What do I mean by outcome? Essentially, we have two outcomes, poor and good. Poor refers to the death of the patient or her transfer to an intensive critical care unit. And good refers to the release from the hospital or to the admission to their care units. From a mathematical point of view, this is a very classical classification problem. So we are given the vector of covariance for each patient. And based on this, we want to predict the outcome Y using a score S, which depends on X. The idea is that the smaller S, the less likely the outcome will be poor. And S is estimated, is trained, is the output of an algorithm which is estimated, which is trained on the data. As it is usually done in this context, in order to do so, we split our original dataset in a training sample and in a validation or testing sample. So instead of turning to a given algorithm, we decided to turn to the superlearner ensemble algorithm. So the superlearner is a meta algorithm which takes as input a library of base algorithms which are defined by the user. And then it performs a cross-validation procedure to estimate the performance of each of those base algorithms. So at the end, the superlearning procedure gives the best performing algorithm as assessed by a formal procedure, and so it can be used to pick the best algorithm, which is called the discrete superlearner. And it can be shown that under a mild condition, the discrete superlearner is asymptotically as good as the best algorithm in the library as decided by an oracle procedure. So there is an R package which implements this method. We change the package a little bit in order to take into account missing values. As a performance measure, we rely to on the area under the curve, the AUC. I remind you that the area under the curve tells you the probability that the score of a randomly picked patient with a poor outcome is greater than the score of a randomly picked patient with a good outcome. And we rely on the superlearner, as I said, because it's easier to interpret than other alternatives as the continuous superlearner, which I'm not going to discuss here. I do not have time to discuss how our base algorithms are built. In general, they are the composition of 4 ingredients. We start by applying to our data an imputation algorithm, which allows to deal with missing value. Then we apply a data enrichment algorithm. Then we screen our variables to filter out variables which are not interesting from a clinical point of view. And this is not data-driven. This is an expert decision. And then finally, we apply a main classification algorithm. So our library at the end consists of 130 algorithms. And we consider as main algorithms algorithms such as decision trees, random forests, XGBoost, which is an extension of random forests, and penalized elastic net regressions. So all those are very classic algorithms. The innovation is that we put them together in this superlearner procedure. As I said, training the superlearner requires to perform cross-validation. And once we have the superlearner, we rely again on an external layer of cross-validation to estimate its performance, its AUC. So the cross-validated AUC of our procedure is 83%, which is fairly good in machine learning. And interestingly, it turns out that many times the best performing algorithm results to be a random forest. So this is the AUC together with the ROC curve. So the AUC is can be defined also as the area under this curve. And as you can see, there is a problem with sensitivity. For a larger value of specificity, the sensitivity is not very good. So let me show you some more details about this. So here you have the scores. Here you have the patients with poor outcome, and here the patients with good outcomes. Now we decide that a patient will have a poor outcome if the score exceeds 0.5. So essentially, all these patients will be correctly classified, and the proportion of correctly poor patients is the sensitivity, so 60% in this case. Whereas all these patients here who are good are classified as good patients, and the proportion of such patients is 92%, which is very good. So the problem is with sensitivity. And as you can see, essentially we have a problem with this group of outlying points for which we cannot give a good classification, a correct classification. So I'm not going to talk about the first goal anymore. So let me switch to the second aim. So the second aim is to try to define the importance of a variable in the evolution of the disease, not relying on a model. We do not want to rely on a model. We want to have an agnostic measure of importance. And once we have such a definition, we want to estimate this quantity, possibly together with confidence intervals. And in order to realize this program, we turn to the targeted learning framework. Just a quick insights about targeted learning. In applied statistics, very often you pick a model for analyzing your data based on the outcome type. For instance, you have data with a binary outcome. In this case, you will turn to logistic regression, which is a classic method for binary outcomes. Then you fit your model, and you look at the coefficient of a given variable, and you say that this coefficient will quantify the importance of this variable. Of course, this approach is flawed if the model is not the one generating the data. So under model misspecification, you have a problem. So from a mathematical point of view, it makes much more sense to first define a measure of importance of a variable, and then to try to build an estimation strategy that targets that quantity without relying on a specific model. And this is exactly what the targeted learning methodology proposes to do. In particular, it allows to estimate those target quantities, using machine learning. And in turn, you will have estimates which are much closer to the real parameter than estimates obtained using standard parametric models. And this allows in turn to have estimators which can be proven to be Gaussian. And this is very important in statistics, because then you can compute asymptotic confidence intervals and do tests and compute p-values. So what is the important measures we decided to use in this project? So we adopted an importance measure which is known as NPVI, which was introduced by our colleague Antoine Chambaz earlier in literature. Essentially, if P is let P be the law, the joint law of X and Y, where X is the vector of covariance and Y is the outcome, and let Xj be the variable of interest. And we make the assumption that the variable of interest comes with a reference value or a reference interval. And this is very often the case in medicine. Imagine, for instance, that Xj is the heart rate. We can take as a reference value or reference interval anything between 60 and 70 beats per minute. So this is a reasonable assumption in medicine. So now the NPVI is defined as the slope of the linear regression of this risk difference against this difference here. So this difference measures the deviation of xj from its reference value, whereas here we have a difference in probability, so it's a risk difference, and it measures the difference between the probability of having the poor outcome given a full set of covariables minus the probability of having the poor outcome given the set of covariables in which the variables of interest, the variable interest is fixed at the reference level. So it measures how a deviation from the reference value correlates with a difference in risk. So for this NPVI measure, an estimation strategy has been built. It is already known. This relies on the superlearner again, and there is a package, an R package that can be used to estimate such things. So I quickly show you some of the results we can get. So here you have for each variables or for a selection of variables the point estimates of the importance measures together with confidence intervals. So all variables have been normalized, and when the importance measure is positive, as it is the case for these variables, it means that when xj exceeds the reference values, the risk grows, okay, which is reasonable. If you look, for instance, at this variable here, which is the temperature, we know that if the temperature gets higher, chances are that the patient is getting worse and worse. So to wrap it up, of course, we are not the first group addressing this problem. As you can imagine, it still is a hot topic these days. There are several papers that have been published that tries to predict the severity of the disease. The originality of our work is that we try not to rely, as said, on a predefined model and a method for prediction and for assessing the importance of a variable. In practice, as I said, our classifier has a good specificity but not so great sensitivity. So this could be used to identify patients that deserves to be followed up. We have developed a kind of interactive dashboard using the Shiny package, and this is still an ongoing project, but we hope to be able to submit the work soon to a journal. And I show you some references here. Thank you.
Okay, excuse me. Guillermo, do you want to ask your question by yourself?
Yeah, sure. So many thanks, Vittorio. Great talk. So I was wondering, have you been able to implement this model like in a real world scenario, such as a hospital or something like that?
Not yet. As I said, we have an interaction tool, or at least a prototype. I can show it to you if you. I just have to change of. So can you see my
yes.
new screen now? Okay. So so this is the prototype of our tool. So here the medical doctors will be able to insert information about the patient, and in turns here you have a score. Okay, but we haven't tried yet in a real setting. To be honest, this is very from a mathematical point of view, this is very exciting. When it comes to the real practice, I think there are regulatory problems, because in France this will be a so-called medical device. So this will, I think this will require some authorization. And it might be that it needs to be its efficacy maybe needs to be proved in a trial. So I think this will require further work, which is not mathematics. It's more clinical research.
Okay, thank you.
Okay. There are two other questions, so please, Vittorio, short answers, please. Hector.
Thank Vittorio, nice question, very, very sharp method somehow. I just want to know if COVID itself is used in your method. I mean, there are some specific things about COVID that you are using in your classificator, or this could be applied to any other problem that has some kind of a structure?
This can be applied to any other problems. The only part in which we applied COVID knowledge is when we screen. We ask. I wanted to show my presentation, but it disappeared. So okay, I stopped it. We asked our colleagues to point to usual suspects, so covariates that makes sense from a clinical point of view to reduce the dimension of the problem.
Okay. A second question, because it's very related to that, and so in that part, things like comorbidity appears, because I didn't see comorbidity in your variables. I mean, you know what comorbidity is?
Yeah, but comorbidities are there, definitely. Yeah.
Okay. Thank you.
Just to add this kind of question, so you used it in real time during the pandemic. Do you want to use it, or do you have intent to use it now with more data than you could get to check? I think about the first part of your talk. Do you want to use more data to check that your method is very, very efficient?
Yeah, definitely. So the idea now is to try to validate it on external data which were collected after the data we relied on. Yeah.
Okay, thank you. Clémentine, do you want to ask your question?
Yes, thank you for the talk. I have a question about the NPVI importance measure, because it seems close to total sensitivity indices or mean decreased accuracy for random forest. Is there, but for these measures, you don't choose a reference. So
yeah. I'm not sure. I must admit that I don't know this score you are mentioning. So this is something related to random forests?
Yes, for example, if you do classification with random forests, but it is also related to total sensitivity measures. But the difference is that here you have to fix your reference, so it may be difficult to fix. And with the measure I mentioned, you take the mean over all the references you can consider.
Okay.
Thank you.
Thank you. I think we stop here because we are running out of time. Thank you, Vittorio. The next speaker is Jocelyn Dunstan. Sorry, I'm not sure I'm pronouncing it the good way. Is it okay? So she's from CMM at the University of Chile, and she will speak about natural language processing. One more time applied to clinical decisions. So please, Jocelyn, the floor is yours.
Thank you very much. And welcome to my talk about, as I said, natural language processing in the context of medicine. And more generally, we could talk about artificial intelligence affecting or impacting medicine in at least 3 different ways: in computer vision, in robotics, and what I'm going to talk in natural language processing. And this is a handwritten prescription, which is hard to read for everyone and machines, But even though when this is written in the computer, it's not much easier to analyze. And it's because natural language in medicine has some characteristics, which are, there is a heavy use of standard abbreviations. And this is, it's not just in Chile, it's a universal phenomenon. And it's because medical doctors are there to treat patients and to check diseases and to touch the body, not to write poems or like long text. It's very different to write a paper about a clinical case that to be with the patient, especially in public settings or public health care, where there is short time in general. So there is non-standardized abbreviations in huge amounts. And also there is a lot of difference between writing for a patient when you are a specialist, for example, an oncologist, and you have more time and it's very specialized versus to be in the urgency, for example, or in the public healthcare system. It contains important information. Someone could say, well, if there is a menu that you could choose, maybe that's the end, like to have a good, I don't know, like a web page where to enter the electronic health records. Maybe if it's good enough, you don't have to write in clinical text, but the reality is that there is always important to give a space for the practitioner to write what couldn't be recognized or recorded somewhere else. Also, there is restricted access by privacy law, and this again is very universal, both in Chile and in France. There are laws that don't allow to see or to work very easily with this. In fact, I'm going to France in January, and I need to apply to the defense because the lab in France has electronic health records, so I have to prove that I'm not going to do anything with sensitive information. And lastly, annotated corpora means a text that has been labeled or classified according to clinical information, has important or certain type of patient, but also annotated corpora, which I will talk a bit more, means a text, someone with clinical knowledge can write down, this is a disease, this is a medication, this is an annotated corpora. Unfortunately, annotated corpora and tools are most of the resources out there are in English. So there are theses in Chile happening right now that are for the English language, because it's the most resource language. So we both, the French and the Spanish suffer from this. And actually my colleague that I'm going to visit in January, Aurélie, wrote this important paper when she writes about what are the opportunities and challenges for clinical natural language processing in languages other than English. So now I'm going to talk about what we have been doing in Chile, and I will try to be brief. I'm looking at the time. I have 6 minutes left. So like 3 years ago, I found a place where to do research on clinical text, because in general, it's hard to obtain text, and it's harder to then publish papers where you share the corpus or the text. But there is something that is called the Chilean waiting list. And it's a national registry. In Chile, 75% of the population is in the public healthcare system. And there is a reason for referral, like why this person needs to see a specialist. And the reason why they are in the waiting list is in free text. And this national registry can be accessed through transparency law. In Chile, any Chilean can request public data, and this is considered public data. So a couple of years ago, I wrote to every healthcare service in Chile, there are 29, requesting the public, this waiting list, which is public information. So in that way, I got 5 million referrals. And this this work, I mean, this requesting the public data was which has allowed my group to publish several papers on using clinical text. And which is really nice is that it's real clinical text. It's written by the practitioners in a public healthcare system. Because other groups, for example, in Spain, they have to use papers written by medical doctors about cases, which is very different to the reality in the consultation. So the groups, I mean, the question that we have as a group is, can we improve the management of this waiting list? I don't have time to tell you, but it's a waiting list with a lot of waiting time. So it is a national problem, this waiting list. So can we use natural language processing to improve in some way the management? And a second question, which is very important, is can we have a secondary use of this information? For example, to calculate the incidence of diseases. So one of the first things we did was in the topic of text classification, and we wrote a paper about how we could classify patients which belong to one waiting list that were misclassified in another one. And I know that the group in France has a very similar paper on a hospital in France. So this is purely text classification, giving a referral, this belongs to this class or to the other class. The second is this annotating corpora, and this is written in Spanish, but here you can see that says cáncer de colon, like colon cancer, and someone with clinical knowledge could see that this is a disease and that colon is a body part. So we do this for like now our goal is 10,000 of these referrals annotated to create the Chilean waiting list corpus that we have called, and we have published already some parts. This is what I mean by having an annotated corpus which we want to share. So this is very important, to be able to then put in the community this resource. And these are all the entities we have. We have body parts, medications, abbreviations, and procedures, and all that. So this is actually it's difficult to do this because you need the text to start annotating, but also you need clinical people with clinical knowledge to do that. And also you need like a procedure, like a guidelines for the annotation, and also like a method to compare the annotation and be sure that it's consistent. So that's why it takes many years to do. And we have models for this task in NLP that is called natural name entity recognition. That a neural network can, from every word in a sentence, classify if they belong, for example, to a disease or not. So from a text, understanding if this text contains diseases or medications is nice and important, but more important will be to codify diseases, which means one thing is to know that this is colon cancer is a disease, but like assigning a code from international diseases could be even more important, because that allows you to, for example, compare the incidence of some type of cancer in Chile versus another part of the country or another part of the world, or calculate the cost of procedures and diseases. So we have been working that with the Fundación Arturo López Pérez, which is an oncological foundation in Chile. So here you see an example. Here it says cáncer de tiroides, where tiroides is a part of the body here. And here it says there is the type of cancer and the code, and then there is the location of the cancer, or topography, called in medicine. And this project that lasted 6 months, led by CMM, now has a web page that is open to the world, and you can write down some examples. For example, I wrote a patient with colon cancer, and it tells you with the probability what type of morphology is, and it gives you, and also the topography. And it allows you also to see other results, and for example, check there is another disease or another topography And in that way, the system can improve itself with the time. And finally, at the beginning, I told you it's important to measure, for example, the secondary use of information, for example, to measure the incidence of diseases. So all my work actually goes to, at some point, maybe 2 years more, be able to have a web page or like a dashboard where someone could see what is the picture of the diseases in Chile. Like everything what is written in free text could be codified, and you could, like, for example, choose a disease and see how what is the distribution across sexes and ages and in the regions. So we did that as an example for psoriasis, which is a skin disease, and there is a global atlas initiative because psoriasis is not clear how many people in the world are suffering from psoriasis. So we used the national waiting list to study this. And we were able, for example, to study the distribution across latitudes, because Chile has a very different exposure to the sun, and dermatologists know that in case of the psoriasis. So we were able to publish this paper where we study a bunch of things, including the latitude relation. And with that, I finished this the part of my group that dedicates to natural language processing at CMM. And thanks very much.
Thank you. Are there any questions?
Excuse me, I have a question. I don't know how to raise my hand.
You have to click on reactions, but okay, you can ask your question.
Okay, well, thank you. Sorry. Thank you very much, Jocelyn. Very, very interesting talk. So natural processing and natural language is a very well-studied problem in the industry, right? This is a general problem. So I was wondering if you compare your accuracy in your results with more commercial software that might be available, maybe for other purposes, but that can be adapted to medicine if you compare the results.
Yeah, but sorry, you said that the NLP is a task addressed by the industry, or not so?
No, I meant that in general, recognition, but based on artificial intelligence of natural language is in well study. I don't know, for banks, yeah, for call centers, for other purposes, but I wonder if you can adapt those.
Yeah, no, totally. So I wanted to make sure that we both agree on that. The way that the natural language processing has increased its performance due to transformers and there has been late developments has allowed, for example, retail industry to answer by bots instead of like having people behind. The problem with clinical text is that there are domains in language. There's the law domain, or the, I don't know, the Twitter has its own language or whatever. Clinical text has a lot of ways to write the same thing, and the text is not so openly available. So in general, the system that try to automatize the analysis, they don't work so well because the text is very particular and there is not so many texts to train the algorithms. So for example, the Chilean government now uses a model developed in Argentina, and we have never tried, I mean, because it's all a bit unknown, we don't have access to what are the training corpora or how good is the performance. We don't know exactly how it works, what the government uses now, because it was trained in another language, and we don't know exactly with what models. So I think that there is an opportunity for improving that, especially because now in Chile, many things that require text, or they are managed by text, they are done by human resources. Like all what I told you about this, trying to understand if a patient is misclassified, is done by a nurse in every hospital in Chile. There is no machine there.
Okay, Thank you. Another question by Francisco, please. Quick question, quick answer.
Sorry. Yeah. So thanks, Jocelyn, for the nice talk. I love the idea of the dashboard. So I have a question about the latitude plot. So do we know what is the mechanism that produces psoriasis? And I was wondering whether you could plot UV exposure, because if you take into account the ozone layer hole, this could look different.
Yeah. So psoriasis has many roots, including like stress and genetic background. But the sun is the UV, as you said, is the UV radiation, and some people can model the amount of UV according to the latitude. There is like a formula for that. And actually, the original paper we checked was from England and from the UK. And the UK is such an island. I mean, it's this size and it has like 4 latitudes different, and Chile has 40. So yeah, that's why we study in Chile.
But they don't have an ozone layer hole.
No, so we didn't include the ozone layer, and that could be nice to include.
Thank you.
Okay, thank you. Thank you, Jocelyn, for your talk. We switch to the next one. The next speaker is Emile Shida. Are you here?
Yes, can you hear me?
Yes, can you share your screen, please?
Yes.
So we are coming back to France in Clermont-Ferrand, and Emile will speak about think, and she will speak about big data in astronomy, I think.
Yes. So thank you very much for the invitation to talk today. It's good that there has already been some introduction to my subject, so I will be able to go quickly. So my name is Emily. I am in Clermont-Ferrand in the middle of France, and I'm going to talk to you about one of the think brokers, about the think broker, which is one of the brokers for the Vera Rubin Observatory that was mentioned before. So I was not sure exactly how familiar with the astronomical data you were, so I'm going to make a very deep introduction about what exactly is that we're looking at. So LSST, or the Vera Rubin Observatory, one of the big things about this survey is that it's a very big camera that will make a movie of the sky. So it's going to go through the same parts of the sky many times, and that would allow us to see what is changing from the previous visit to now. So it's a huge power of studying transients, which we call anything that changes in the sky. So for the purpose of what I'm going to talk, we are always going to be talking about this type of plot, which is brightness in the y-axis as a function of time. So everything that you say something going up and down, this is because the object is getting brighter and dimmer with time. So this is basically the data that we are going to be working with. And there are many things that change with time. You can have stars that vary in brightness. You can have cataclysmic events like supernova, which is something that explodes, or you can have objects that pass one in front of the other, like an eclipsing binary. And in this sense, whenever one object passes in front of the other, you have a little dip in the brightness of the ensemble. So all of these things is just like us as observers from Earth looking at something whose brightness is changing in the sky as a function of time. So I will not going to talk too much because this has already been said. The point is the LSST is going to be a very big telescope. It's going to generate a lot of data. And what is the main path that this data is going to have? So as I said, the point of making a movie is that you see what happens differently from your last visit. So you took a picture yesterday and you took a picture today, and you see that something is different in that point of the sky. Every time you find something different, you generate what we call an alert. So this is a small piece of data that says there is something different in this specific point in the sky at this specific point in time. So the telescope observed this, and this generates 10 million alerts per night, which means that each night there's going to be 10 million potential things that are interested. Those things are going to be sent to brokers. I'm going to talk about Think, but there are others. Francisco is going to talk about alerts in the next session. So you send these alerts to the broker, and the broker will have the very fun job of separating what is interesting and what it's not, and sending this to the users, which basically they only want the interesting ones. So we have to make that filtering. From the data science perspective, this is a huge big data problem. Think is based on distributed computing. I'm not going to talk about that because I don't understand that part. But once you have the data, you use machine learning to actually go through the data and separate and classify specific interests that are good for the user. Basically, this is what happened. There's a lot of data. The broker needs to separate and deal with this thing that is coming to and this is like orders of magnitude bigger than the current telescopes that we have today. So, and because the data is so big, so nowadays most of the telescopes, there is not too much restriction on who can receive the full data stream of the telescope. But with LSST, the data stream will be so big that you cannot. There's a limit number of streams that is going to be distributed throughout the world. So this decision has been made recently. There's going to be 7 of them. So we have a few in the US. In Europe, we have Lazar, Ample, and Think, and Alerson in Chile. So Think has a very specific target. So we have we are a diverse community, but we work in modular in a sense that we only implement things that our community wants. So the structure of the broker was built to be very modular. So we do many things, but I'm going to very briefly talk to you about supernovae just as a case study. But keep in mind that this is just an example of what is possible to do. So the supernova classifier that there is in Think works with combining two different strategies. One is a deep learning strategy based on the supernova. So we have a deep learning based classifier, and the other one is based on active learning. So active learning starts with the hypothesis that your machine learning classifier will just be as good as your training sample is. So the task is to choose the best possible training sample for your model. At each iteration, so here you have your initial data sample. You start with a training sample, whatever you have. You build a machine learning model. You classify your target sample, and then the algorithm will search within the objects for which you do not have label, which of these objects would be informed to your model in case you had the label. So you identify which one of those objects are there and put them back in the training sample. This is super important for astronomy because LSST is going to generate all the kind of data, but it's only features, meaning we are going to have many different types of photos of the sky, but in order to classify each source, we need observations from spectroscopy, which is different telescope, and very, very, very expensive, and we do not have many of those. So getting labels in astronomy is a very big problem. We have been doing this, so while LSST is not live, we have been doing this with the Zurich Transient Facility, which is a current telescope in the US. And we have been doing this since November. Yeah, since November 2020, we have been using this type of system to classify the alerts, and we publish the things that we think are supernova in a website where people who have these other type of telescopes that are necessary to take labels, they check if they can choose those and choose to follow up or not. There's a lot of caveats in this number. I do not have time to tell you why you should be very careful about this slide, but you can ask me in the questions. The main idea here is just that it seems to work. Like most of our targets are that were confirmed were supernovae. 82% of them ended up to be 1A, which is very good for supernova classification. So just to remember, I think astronomy is a very, very fertile ground for machine learning applications, especially because astronomical data, most of the time, they are public. If they are not public exactly on the time, not exactly when they are acquired, but after a certain time, proprietary time, the data becomes public. And the alerts specifically are completely public. So anyone can develop algorithms and methods about this. The difference of Think is like it was designed with adaptive learning in mind. So we made Think because we wanted a system that was able to learn in this loop and provide better classifications as a function of time. So it's very friendly for deep and adaptive, especially adaptive learning methods. And especially for Chilean and French community, we will have a full copy of the data at CCI and 2P3, so in Lyon, and Think is hosted in Lyon. So for Chilean and French researchers who have access to data rights in these first years of the survey, we can also, we will have a private stream where you can compare and cross-match your the things that comes with the alerts with the data that you have from the telescope. Again, I would just, to finish, I would just like to tell you that there has been, I talked about supernova just because it's the example that we have, but many other science can benefit from the resources and the data and the access that that's available. So this is, I think it's a good opportunity for interdisciplinary collaborations to be developed. Thank you.
Thank you, Emile. Just one short question from me. So at the end, you said that the data will become open data after a certain time. Do you have any idea of the certain time?
I don't know for LSST. I don't know if LSST has decided that yet. Probably has, but I don't have that number. I'm sorry. But what I meant is that traditionally in astronomy, this is what happened. Okay. After a while, the data becomes public. I'm not sure if Francisco or someone else have that number, but I'm sorry, I don't have it right now.
No, I don't know. But the alert stream is automatically public. But that's like 1% of the data. Yeah.
So, and the fact that they become automatically public, it's a rule, a law. Who decide this? Just the researchers, or just the people who have obtained the data, or it's?
So as far as I understand, each telescope works on, has its own, each collaboration has its own rules. I don't think there is a general thing to decide that.
Okay, thank you. Are there any questions?
Can I ask a question?
Yes.
Thanks for the great talk. So I'm curious, you're sending the alerts directly to TNS without human inspection? Is that what you said?
Yeah, so we have a classifier that was trained using the active learning. We send them as candidates. Only the ones with higher probability, right? The ones with high probability are sent as candidates.
And have you tested how many of those are bogus? I mean, do you have like?
Yeah. So with the tests that we made, with the alerts that we had labels, we are getting purities around 85%, more or less, in our results. But, and this is why I said you need to be careful with that slide, is that we take all of our candidates, we send this to TNS, which is a website where people scroll to find things, but we cannot avoid that there is still a human. So before deciding to take a label, there is a human that looks at the light curve. So it looks at the data, and this person is going to decide if they are going to follow it up or not. So there is this level of screening that we do not have access on how to model. That's why I said we should be, there are caveats on that number. This level of human interaction, because for example, if we had for the screenings that we made within our team, we find that all of our candidates, they look like things. But if there were some bugs that is obviously nothing, that's obviously not a good candidate, a person looking at the data would not decide to take a label of that thing, right? At this point, the whole process is still not automatic.
Okay, thank you.
Thank you. Other question?
Yeah, can I add a question?
Yes.
So do you have an idea of how many interesting signals are not labeled as candidates? So it's the opposite question.
Yes. Yeah. So this is one of the things that in this thing are most different from the others. So we call this efficiency, right? So if I have 100 objects in my sample, how many of them I correctly classified, how many I lost? For this classifier, efficiency is around 35 or 40%. So this means that there are many things out there that are probably candidates that we do not get.
Mm-hmm.
But this is a choice, because we could have, like if you increase the efficiency, you will lose on purity. So this is a choice that we made when we developed the algorithm, that we would have a higher purity in our sample, but as a in the counterpart, we have a very low number of candidates.
Mm-hmm.
Okay, thank you. So thank you for this wonderful talk, and we are coming to the next talk of this session by Rodrigo Abarca del Rio. Sorry for the accent. So Rodrigo is from Universidad of Concepción, and so we will come back to Earth. His group is looking. Is specialized in the Earth observation, and Rodrigo will speak about data for environmental and geophysical analysis.
So you are seeing my
yes,
data sharing? Okay, super.
Yes.
So I am before the coffee break that everyone is doing at home. So we have a little time, so I'm going to try to be short, as fast as possible. So this is the students involucrated there. It's Maria Pedrero, Caris, Ignacio, Fernanda Lopez Valia, Oscar Parra, Lara, and Figueroa, which are the professor, and we have external collaboration. So the main problem we are facing today is that you have many satellite missions. There is like, if you don't know, maybe it's like on Earth, it's like 3,000 mission satellites surrounding the Earth, with, of course, many of these, like great percentage will be from the defense of the telecommunication industry. So the problem is how it is possible to handle all this data. It is not possible. Even more, there is not enough people to analyze all this data. It is almost impossible to analyze this data. So in collaboration with the people from different faculties and within our university, as well with Lagos in France, which is a lab specialized in satellite data, with NES, Météo France, and 2 universities in the US, we decide to mount something like a collaboration to create software to analyze this kind of data. So we have many groups working in there, and because of the time on water and solid earth and disaster warning and cryosphere as well as in energy, but I'm going to just to present some of the flowers in water and solid earth. In water, what we are doing is mostly concentrated regarding the forthcoming SWOT, is a satellite. It's a mission that is going to be launched in 2022. The satellite will have a pixel of about 100 meters, which is not very high in surface, but with it is ultimately, which is it's very very high compared to what is done actually. So just to have a look, and I'm in charge within the satellite of South American lakes. And you can see in this image, so I am going to make you travel all around South America. It will be changed a little. So in the upper part of this image, you have all the lakes in the earth, and here is the main lake depth. And you can see there that there's many lakes on earth, and there's millions of lakes on earth. And in fact, there's very little treated. There's the number of lakes that are known and that are treated or are investigated on earth are not more than 300. So there's a lot of work for doing that. And there's a lot of place for doing that. Even the rivers are very little treated. But with this satellite, it will change. So I am in charge of treating this lake with collaboration with many persons on South America, in Argentina, in Bolivia, in Peru, in Brazil, and so on. And what I'm going to show is some variability, what's going on in the certain lakes here or in the north of this part. So one of the big problems with the lakes, and here it's a case I'm going to show you here, is that we don't have information of what is going on. So this is a very little, not lake, lagoon, close to Concepción. So here is South America, here is Concepción, here in this little square here, and then within this little square, there's another very little square. It is called these two big little lakes. Concepción is over here, the city, okay? And these lagoons are not longer than, let's say, 3 kilometers with like 30-meter depth and so on. And this is all the information you have in there. So this is the temperature measured over the lake. And this is one of the lakes most measured in Chile. Okay, and you can imagine that everywhere on Earth, it happens the same. So instead, you have a lot of information coming from satellite. For example, here you have the information we could rescue for Landsat 7 and Landsat 8. Just yesterday, they launched in America the Landsat 9, and you can detect something like there's maybe from all this year, like you could have like 600-700 satellite image. Each one of these satellite images is like 120 megabytes. So it's a big amount of gigabyte to treat. So it's not possible to treat all this data. So using what maybe you know is Google Earth Engine. Google Earth Engine has a lot of data in the cloud. We could treat all this satellite data, and we could compute for this very little lagoon with different methods, and as well with, but not machine learning in this case, just with a monthly means, a median average, some standard deviation. This is a very simple thing. We could compute the surface temperature over these very little lagoons. So the idea now is to compute over the whole South America, or to provide to the people that are interested this very little software in Google Earth Engine. Of course, this will be improving in the forthcoming month, and this is a paper under review in remote sensing. Another problem we face in South America, and now we are moving to another place in South America, is we are moving to Lake Maracaibo. Lake Maracaibo is in the northern part of South America. It is there. It is in Venezuela. and it is the greatest lake of South America. The problem with this lake, it is a very high polluted lake. It is a very high polluted lake because, of course, our surrounding the lake is the petrol industry, the oil industry. And moreover, we don't know if it's related or not. There's an increasing amount of algae within the lake, and this algae moves with a circle. You know, there's a circulation in the lake, and this algae moves. So create as well a software to treat this data with information this now with Landsat and MODIS satellite. So there was what we call conventional remote sensing, and now the modern remote sensing. With the conventional remote sensing, you have to download each image. So it's like 100 or 200 megabytes, and try to treat 100 images. It may take years to track that data. Actually, with Google Earth Engine, but there's others engine in Amazon, and I know now that as well there is engines that are being prepared from Copernicus in Europe by private companies like Airbus and so on. So there will be like many alike Google Earth Engines softwares or that provide computing power and storage. So for constructing over just 10 years, we have like for 70 years, we could have used 500 images. It is impossible to do. But with this kind of information, or with this kind of information that is available through the web by Google Earth Engine, it is possible. And we could construct by many methods what's going on in Lago Maracaibo. And the idea was then to do the same for other lakes, or to provide the Google Earth Engine software to the community. Another thing is when you treat lakes, and because of the global warming thing or the problem we have in Chile, is that you have to try to understand what is called the lake water balance. I mean, what is the water incoming, and what is the water outcoming from a lake. And in this case, we choose to treat a lake which is called the Popo Lake. The Popo Lake is located in the southern part of the Altiplano. It is connected to the Lake Titicaca through a river which is called the Desaguadero. Of course, if you talk in Spanish, the Titicaca connected with the Popo by the Desaguadero, it makes you laugh because it's something special. You can note that, for example, here in April 2013, the lake was almost full, not totally, but in January 2016, the lake was totally dry. It was a big problem because there were communities there that live on the fish. Even though the fish there or the water is highly contaminated by the mining industry surrounding this lake. In fact, we don't know actually why this lake dried up, or it collapsed. So there's two possibilities, or at least maybe four. One of the possibilities is that we know now that the water incoming from the Lake Titicaca has been now taken by the agriculture. So there's less and less water coming by the Titicaca by the Desaguadero River. So there is less water. Moreover, always a lake is as well dependent on the underground water. And the underground water is being sucked away by the mining industry, which use a lot of water. And moreover, actually, you know, there is climate change, or there's increasing temperature, and the temperature increasing implies that there is more evaporation on the lake and evapotranspiration along the basin. Actually, with satellite, with altimetry, so I mean a satellite which measures send something like a message to the surface and then collects this information, and with the connection with the GPS and so on, it is possible to determine the water level of a lake, the same way you determine the water level over the ocean. So here to the left, you have the water level on Lake Popo. As well, because you have image every day or every month or every 10 days of from satellite visual image, you can determine water surface variation. And because we knew in January 2016 that the whole lake had disappeared, it was possible with this water surface variation and information from laser satellites with the water volume variation. But more than that, actually, it is possible to compute a water balance, and all this information that I'm going to describe here, so level of the lake, superficie, fluxes, river fluxes, this is with the oncoming satellite mission, evaporation from the lake, evapotranspiration from the basin, the precipitation is actually almost all made by satellite, and underground water with soil moisture in the surface, but as well information from another gravimeter satellite that is called GRACE. It is possible to have all this information, and you can compare this information with atmospheric models and hydrological models, plus in situ data. And with that, the point is to try, this is what is going on elsewhere, the same in other countries and other continents, is try to understand what's going on in the lake. So our next step is to provide, and this is work made by another PhD student, Ignacio Garcia, who's trying to compute in Google Earth Engine a system that will allow to compute all source automated, mixing all the information from satellite and the information atmospheric model and hydrogen model to compute the water cycle of some South American lakes. Okay. Now we move to solid Earth, and in solid Earth we concentrate in two things. What happens when there is a catastrophic event? For example, what happens when earthquake and tsunami of 2010 took place just in front of Concepción, Chile? Well, this is one of the very well known, was one of the most catastrophic events that took place in the world in the over 21st century, but as well, we take into account all the information we have over the one hand of the last century, was a very strong earthquake followed by a big tsunami. And it was a very strong catastrophic event. And I live in Concepción. The earthquake took like 3 minutes, and it was terrible. So there was a lot, there was a disaster zone. When a catastrophic event like this one, or like inundation, landslide, or whatever, all satellite mission on the Earth free their image, maybe private, not the following days. So it's possible to obtain information from the satellite. The problem is that then you have to detect the change. So we're actually creating a software, also in Google Earth Engine, but as well with Amazon, and with R, with a free software, in where we test on time in the actual level different machine learning methodologies that are expressed there, from deep learning to machine learning.
Time's run out. Please, could you conclude quickly, please? So
finally, at the end, is that we are analyzing many machine learning methodologies for investigating what is going on in the with the satellite to provide this to the South American person working Earth sciences. Okay.
Thank you. Any questions?
Can I ask a question?
Yeah.
Yes, Guillermo.
Yeah, so thanks, Rodrigo, for your great talk. So I'm wondering, from a data-driven sciences perspective, what are the next steps? What would you expect to be happening with this project, let's say in 1 or 5 more years?
Well, the problem is that in South America, we have a very little collaboration. So there's, I don't know the number of persons that are working with data-driven science. So why I'm presenting here is because I would like to find collaboration with people working data science. For example, I saw the presentation by Emily Ishida. I'm interested in finding what can be done with other persons here, because we in geophysics we always work with the geophysician. This is a problem. I mean, of course, the people working in remote sensing are very good person, but there's many groups worldwide. So, in fact, we are looking for collaboration with that may enhance our capacities.
Okay, thank you.
So coming to here, I hope to find the person with whom collaborate to extend the possibilities of remote sensing to other fields, or the inverse, in fact.
So thank you. I think we will stop here. Thank you very much to all the speakers to this session. It's written that we have a 30-minute break for coffee. I'm not sure that you will use all this time. So perhaps we can come back as it's written in the schedule. What do you think, Hector? So we could come back at 11:30 in Chile and 4:30 in France. Is it okay for you, Hector?
Yeah, I think it's better. Yeah, I think it's better. So we also can finish more or less on time. So yes.
Okay.
I prefer that. Yeah.
Okay. So we come back.